At 02:10 and 5 seconds UTC, an Airbus A330 cruising at 35,000 feet above the Atlantic lost reliable airspeed data. The autopilot disconnected. The pilots took manual control in darkness, turbulence, and cloud. Within seconds, the aircraft began to climb. Its speed fell. Then the synthetic voice called stall. The warning would later sound continuously for 54 seconds. Yet the crew never formally identified the aerodynamic stall. 4 minutes and 23 seconds after the autopilot disconnected, Air France Flight 447 struck the ocean. This is not a story of one frozen sensor. It is the reconstruction of a chain in which technology, training, human perception, and a few critical control inputs aligned. On the evening of May 31, 2009, Flight 447 left Rio de Janeiro for Paris Charles de Gaulle. The aircraft was an Airbus A330-203, registration F-GZCP. On board were 216 passengers and 12 crew members, representing 32 nationalities. Because this was a long overnight flight, 3 pilots shared the cockpit duty. The aircraft took off at 22:29 UTC. For more than 3 hours, the flight was routine. Its last radio communication with Brazilian air traffic control occurred at 01:35. Far from land and outside radar coverage, the A330 continued northeast across the Atlantic at flight level 350. The captain left the cockpit for a scheduled rest. 2 first officers remained at the controls. Ahead lay the Intertropical Convergence Zone, a broad band where warm, moist air rises and produces powerful convective clouds. Thunderstorms here can tower above normal airline cruise levels. The crew used the weather radar and discussed the cells ahead. At 02:08, they selected a heading about 12 degrees left of their original route. Turbulence increased slightly, and the selected speed was reduced to about Mach 0.8. The aircraft was not flown directly into a single visible wall of red radar returns, but it entered an area containing deep convection, ice crystals, and changing air masses. At 02:09 and 46 seconds, the cockpit recorder captured a rising background noise later identified by a 330 crews as the sound of ice crystals striking the aircraft. At 02:10 and 3 seconds, engine anti-ice was selected on. 2 seconds later, the stable cruise ended. An airliner does not measure its forward speed with one simple gauge. Pressure from external probes is compared and processed by multiple computers. On this A330, 3 Pitot-probes supplied the pressure used to calculate airspeed. In severe high-altitude ice crystal conditions, the probe openings could be temporarily obstructed. The engines did not stop. The wings did not ice over and suddenly lose lift. The immediate failure was more subtle. The computers no longer agreed about the speed of the aircraft. Similar temporary airspeed events had occurred before. In 2007, Airbus had recommended replacing the Thales A probes with an improved BA model. After further high-altitude events, Air France decided in April 2009 to replace the probes across its long-range fleet. The first replacement parts arrived 6 days before the accident. F-GZCP had not yet been modified. The ice crystal blockage on Flight 447 lasted less than a minute. A trained crew, keeping a safe pitch attitude and thrust setting, should have been able to fly through that temporary loss of information. But the loss of speed data triggered a far more dangerous sequence. At 02:10 and 5 seconds, the autopilot disconnected. The auto thrust disengaged moments later, and the flight control system changed from normal law to alternate law. Some automatic protections, including angle of attack protection, were no longer available. The aircraft rolled 8.4 degrees to the right. The pilot flying moved his sidestick left, but also pulled back. Over the next 11 seconds, his pitch input varied from neutral to roughly 3/4 nose up. The nose rose. The pitch attitude passed 10 degrees, and the vertical speed climbed above 5,000 feet per minute. At the same time, the recorded airspeed on the left display plunged from about 275 knots toward implausibly low values. The standby indication also fell, but not in exactly the same way. At 02, 10 and 10 seconds, the stall warning activated briefly. The pilots recognized that they had lost the speed indications and that the aircraft had entered alternate law. But the control response did not settle into the known, unreliable airspeed memory values. The correct priority was attitude, thrust, and a stable flight path. By 02, 10 and 26 seconds, the vertical speed reached approximately 6,900 feet per minute. At cruise altitude, that rate of climb consumes energy very quickly. The pilot flying briefly pushed forward. The climb rate decreased, the displayed speed recovered, and the pitch attitude fell toward 6 degrees. For a moment, the aircraft was moving back toward a safer condition. But the situation was still not understood. The pilots were trying to reconcile contradictory speed tapes, flight director commands that disappeared and returned, warning chimes, thrust modes, and an aircraft that had climbed thousands of feet. At 02, 10 and 51 seconds, the stall warning sounded again. This time it continued. The thrust levers were moved to takeoff go-around power, while the pilot flying again held nose-up input. More thrust can help an aircraft recover only if the angle of attack is reduced. With the nose held high, the additional thrust did not solve the underlying problem. The angle between the wing and the airflow kept increasing. The aircraft reached a maximum altitude of about 37,900 feet at 02, 11 and 10 seconds. Its pitch attitude was near 16 degrees nose-up. Then the climb ended and the descent began. The wing was now stalled. At high altitude, a stall is not always a dramatic nose-down break. Flight 447 remained nose-up while losing altitude at an extreme rate. The engines were still producing thrust. The airplane was responding to many of the pilot's commands. But the airflow over the wings was no longer producing enough controlled lift. The warning repeated for 54 seconds. No pilot formally called the stall, and the required recovery, reduced the angle of attack with a decisive nose-down input, was not sustained. Then the warning stopped. This silence did not mean the aircraft had recovered. The angle of attack had exceeded 40 degrees, and the measured speeds had fallen so low that the system treated the data as invalid. With invalid data, the stall warning logic could fall silent. When a pilot briefly lowered the nose, the airspeed values became valid again, and the stall warning returned. In that extraordinary condition, an action moving toward recovery could appear to produce another warning, while pulling back could make the warning disappear. The warning logic was behaving as designed, but outside the situation any crew expected to encounter. At approximately 02, 11 and 42 seconds, the captain returned to the cockpit. By then, the aircraft had descended back through 36,000 feet. Its angle of attack was above 40 degrees, its vertical speed was close to 10,000 feet per minute downward, and its nose remained raised. The two first officers reported that they no longer had valid indications and did not understand what was happening. The captain entered a cockpit filled with alarms, inconsistent displays, and rapidly changing control priorities, without a clear verbal explanation of the earlier nose-up inputs. The Airbus sidesticks are not mechanically linked. One pilot cannot feel the exact movement being made by the other. When both pilots move their sticks, the computers combine the commands unless one pilot takes and holds priority. Dual input warnings sounded several times. For much of the descent, the pilot on the right continued to command nose up. At moments, the pilot on the left commanded nose down. The combined result was inconsistent. The aircraft was not tumbling. It was falling through the darkness in a deep stall, with its nose still closed to the horizon. At 02, 13 and 41 seconds, one pilot finally stated that he had been at maximum nose up for some time. Another immediately called for nose down, and asked for control. There was still no stable recovery input. At 02, 14 and 17 seconds, the radio altimeter announced that only 2,140 feet remained. Ground proximity warnings followed. The recordings ended at 02, 14 and 28.4 seconds. The last data showed a descent rate of 10,912 feet per minute, a ground speed of 107 knots, and a pitch attitude of 16.2 degrees nose up. The aircraft struck the Atlantic almost level in roll and was destroyed on impact. No distress call had been transmitted. All 228 people on board were lost. For investigators, the first evidence was not a cockpit recording. It was a stream of automated maintenance messages sent by ACARS between 02:10 and 02:15. Those messages revealed failures and airspeed inconsistencies, but not the full sequence. French and Brazilian forces found floating debris and recovered the remains of 50 victims in June 2009. Beneath them lay one of the most difficult search areas on Earth, the rugged mid-Atlantic ridge, thousands of meters below the surface. The recorder beacons were designed to transmit for at least 30 days, but no signal was detected. Sonar vehicles searched steep terrain, and multiple probability models were revised. The operation required 5 search phases over almost 2 years and cost more than 30 million euros. On April 3, 2011, the main wreckage was finally located at a depth of approximately 3,900 meters, about 6.5 nautical miles north of the aircraft's last known position. The flight data recorder was recovered on May 2nd. The cockpit voice recorder followed 1 day later. The data transformed a mysterious disappearance into a precise chain of events. The BEA concluded that temporary inconsistencies in measured airspeed, likely caused by ice crystals obstructing the Pitot-probes, led to the disconnection of the automation and the change to alternate law. Control inputs then destabilized the flight path. The crew did not connect the loss of displayed speed with the appropriate procedure. The deviation from the intended flight path was recognized late and corrected insufficiently. The approach to stall was not identified, and the stall itself was never diagnosed. Investigators also identified deeper contributing factors: limited training in manual aircraft handling at high altitude, no practical training for this combination of unreliable speed and startle, weakened task sharing, unclear presentation of airspeed inconsistencies, and the crew's failure to take the stall warning into account. The report did not describe a single villain or a single broken component. The Pitot blockage was temporary. The aircraft remained controllable. The engines continued to run. The final report produced 41 safety recommendations. They addressed pilot training, aircraft systems, operational oversight, search and rescue coordination, and the ability to locate and recover flight recorders after an ocean accident. The central training lesson was stark. Crews must be able to control pitch and thrust manually at high altitude, recognize unreliable airspeed, and recover from a stall even when automation, displays, and warnings create surprise. Flight 447 also forced aviation to examine how machines communicate uncertainty. A warning is useful only if the humans receiving it can connect the sound, the displays, and the motion of the aircraft into one correct mental picture. For 54 seconds, the cockpit heard the word stall, but the crew never understood the condition those words described. Today, the accident is studied not to reduce 4 minutes to pilot error, but to understand how confusion can defeat experienced people inside a highly automated system. 228 lives were lost between Rio and Paris. Their memory remains the reason this chain must be understood.